Hello everyone and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is continuous time filters. In continuous time signal processing, a filter is a circuit, a network of interconnected electrical components such as resistors, capacitors, transistors. They are widely used in electronics and telecommunication, in radio and television, audio processing, computer graphics. In this lesson, we will apply Fourier transform to analyze filters in the frequency domain. Given an LTI system, if the impulse response is h of t, using the convolution theorem, we can find the system's response y of t to any input signal x of t as the convolution of the impulse response and the input signal. This is in time domain. Now, if we take the Fourier transform of this expression using the Fourier transform convolution theorem, what we will have will be a product. In the frequency domain, that is, the Fourier transform of the output will be the product of the Fourier transform of the impulse response h of t and the Fourier transform of the input signal x of t. H of j omega, the Fourier transform of h of t, is called the frequency response of the system. Ideal filters allow distortion-free transmission of a signal for a certain range of frequencies while completely suppressing the remaining frequencies. In a distortion-free system, the output must be a delayed copy of the input or zero. When the output is a delayed copy of the input, using the Fourier transform time-shifting theorem, in the frequency domain, the input and output will be related as indicated here, which gives e to the power minus j omega t0 as the frequency response of the ideal filter. As you can see, the absolute value of h of j omega here is 1. So an ideal filter has constant gain and linear phase over one or more frequency bands, and it has zero gain otherwise. The frequency interval over which the gain is non-zero is called a passband, while the interval over which the gain is zero is called a stopband. And the frequency where a passband ends and a stopband begins is called the cutoff frequency, or a cutoff frequency. The four filter types shown here are the most common arrangements of passband and stopband intervals. Also, a filter that passes all frequencies is called an all-pass filter. Note that ideal filters in practice are not realizable. Consider an ideal linear phase low-pass filter as defined here. You can see the magnitude and the phase when t0 is set to 2, for example, shown here. We're interested in finding the impulse response in the time domain. As you know, the impulse response is the inverse Fourier transform of h of j omega. Therefore, for an arbitrary delay value t0, we have a sinc function as shown here. And the impulse response of the ideal low-pass filter in the time domain is a shifted sinc signal. Now let's consider a sinusoidal signal passing through the ideal low-pass filter that we define as the unit box. The output then will be the inverse Fourier transform of the product of x of j omega and h of j omega. First, let's find the Fourier transform of the input signal x of j omega. Then the Fourier transform of the output will be the product of x of j omega and h of j omega. The inverse Fourier transform will then give us the output signal in time domain. For signal frequencies below the cutoff frequency, which is 1, the input signal will pass through the filter undisturbed, and the output will be a delayed version of the input. For frequencies exceeding the cutoff frequency, omega greater than 1, the output will be simply 0. Now let's look at the response of the ideal low-pass filter to a square wave input, a periodic signal. To find the Fourier transform of the periodic input signal x of t, we will need the Fourier series coefficients first. Note that here omega 0 is 2 pi over 1 or 2 pi. We can find the Fourier series coefficients using the Wolfram language. And now the Fourier transform of the periodic signal will be as shown here. Let's plot the magnitude spectra of the ideal filter and the input signal together. The Fourier transform of the output is given by the product of the x of j omega and h of j omega. And therefore, based on the plot that you see, this summation can be reduced to the sum of these three terms for k equal to -1, 0, and 1. Now that we have the Fourier transform of the output signal, we can apply inverse Fourier transform to find the signal in the time domain, the output signal in the time domain. Since each impulse in frequency corresponds to a decaying exponential in the time domain, we get the value of y of t as indicated here, which can be simplified as shown in this expression. We can also plot the input signal and the output signal together. Note how the low-pass filter removes the signal frequencies in the square wave beyond the cutoff frequency, which is 10 radian per second. Here also you can look at the plot of the input signal and output signal together for varying values of the cutoff frequency. Note that as the cutoff frequency increases past 10, how the output signal changes. Non-ideal filters exhibit both magnitude and phase distortions. Magnitude distortions occurs when the magnitude response within the passband frequencies is not constant. And phase distortion causes the phase of the filter to differ from a straight line. For example, the well-known RC filter exhibits both of these distortions. As we have seen before, filters are modeled by linear constant coefficient differential equations. Given in the general form shown here, y of t and x of t are the output signal and the input signal respectively, and yn is the nth derivative of y of t. Now, if you take the Fourier transform of both sides of this differential equation and use the Fourier transform differentiation theorem, we can get the differential equation in the frequency domain as shown here. We can then solve for the ratio of y of j omega over x of j omega and get the frequency response as shown in this expression. Let's look at this example and find the frequency response and plot the magnitude spectrum of the second order system described by the differential equation shown here. Taking the Fourier transform and using the differentiation property of the Fourier transform, we get the expression shown here. And once we simplify the expression, the frequency response will be the ratio of the output to the input. We can also plot the magnitude and the phase of the filter h of j omega and see how they change over the values of the frequency omega. Now consider an LTI system with an input of the form e to the power j omega t. The output will be obtained using the convolution integral, and if we substitute the value of the input in the convolution integral and simplify, note that the integral is simply the Fourier transform of h of t. And so y of t is equal to h of j omega times e to the power j omega t. The output of an LTI system is simply the input e to the power j omega t is scaled by the Fourier transform of the impulse response h of j omega, evaluated at the frequency omega. This is a fundamental property of LTI systems. As an example, let's look at an RC filter with the frequency response given as shown here, and let's find the response to the sinusoidal input x of t. Given x of t, we can find the Fourier transform of x of t, x of j omega using the Wolfram language, and the output, the Fourier transform of the output will be the product of x of j omega and h of j omega. Once we have the Fourier transform of the output signal, we can use the inverse Fourier transform to find the output in time domain. We can also simplify the output signal as shown here. Plotting the input signal and the output signal together, we can see that the output is a scaled and shifted version of the input signal. Now that we have found the response of the RC filter to a sinusoid, we can find the response of the RC filter to a periodic signal as well. For periodic signals, we have the Fourier series representation as shown here. And now if we apply this signal to an LTI system with frequency response h of j omega, the output signal can be obtained using the expression shown here. Here, using this plot, you can see the RC filter's frequency response h of j omega scales the Fourier coefficients ck's of a square wave. And if you apply a simple RC filter on a square wave signal, for example, and if you look at the plot of the input signal and the output signal together, as shown here, you can see that as the bandwidth of the filter is increased, the output signal increasingly looks more like the input signal. Finally, let's consider a filter with phase distortion. Assume that the h of j omega, the frequency response of the filter, is as given here. Omega c is the cutoff frequency. Let it be equal to 16 pi, for example, so that we can be sure that the first several sinusoidal components of the square wave are passed through the filter. Now assume that we have a square wave input, and let's look at the response of the filter to the square wave. As you can see, as you change the value of epsilon, the amount of the phase distortion, from 0 to 2, for example, the nonlinearity of the filter's phase increases, and you can see visible distortion in the square wave. In this lesson, we looked at the frequency response of a continuous time LTI system, and we saw that they can be written as rational polynomials in terms of powers of j omega. We looked at 4 different types of ideal filters. We went over characteristics of ideal and non-ideal or practical filters. We saw several examples of signal processing with ideal and practical filters. And we finally looked at the effect of nonlinear phase on a periodic signal.